me to welcome you for the second talk of the afternoon session. This is a plenary talk by Ekaterina Shemyakova, who's at the University of Toledo, and the title of the talk is on super Plucker relations, super Ptolemy relations, and cluster algebras.
Best. Everybody can hear me?
Yes.
Yeah. Okay, perfect. Okay, so thank you so much for inviting me, and thank you so much to the organizers for the wonderful welcoming conference, and to all the participants and the speakers. So it's wonderful to be here. I also hopefully would like to contribute some, hopefully something interesting. So let's just go without further ado, go straight to the point. So I'm going to introduce to talk about some geometric results which I obtained together. So some of it based on my work, some of it based on our joint work with Ted Voronov. So these results are towards a big goal, which several groups are going. It's a goal of defining what is a supercluster algebra, and there are several groups working on it, and we are like one of a group pretty much. So and so there's lots of it's still an open problem. Okay, so just to give you a quick idea what's going on. So the current state of art, we have a definition of value of Ovsienko, which was later modified to Ovsienko-Shapiro. So Misha Shapiro is here. So also they have one of the definitions of cluster algebras. And there is another group, I think nobody's here from that group. It's Lee, Mikso, Ranzing, and Shrivastava. So that's another group. They also have a definition. But I think as we see that we're still dissatisfied with the current definitions. There's some good strong points, there's some weak points, and so there's still open problem pretty much, the supercluster. I will explain a bit later on this. But that's the current state of art. Now the question is, of course, you don't maybe not necessarily know what the cluster algebra is, but how to generalize some notion from classical case to the say super case, right? So when Fomin and Zelinsky invented this cluster algebras, right, they obviously looked at different examples which appear again and again in science in different directions of mathematics, and they figured out that it's a new algebraic structure which seems to be worthwhile to introduce. Now, how we can introduce superizes? We can take one of these model examples which was useful in the past for them and generalize it and look at what we have and try to figure out what should be the supercluster algebra. So that's what. And so there's two groups, at least what I know so far, which is working. So there's a group of Greg Musiker, so Nick Ovenhaus, and Sylvester Zhang. So Nick is here somewhere. Yes, Nick is here, right? So their group, they constructed a proposed algebra structure for one particular example, and they are based there for the super Ptolemy relation, which was obtained by Bob Penner and Anton Zeitlin for the sake of those are relations which satisfied by decorated Super-Tuchmuller by coordinates by the global coordinate for decorated Super-Tuchmuller space. So which this relation is coming from there. And so we have a competing relations, which is come from, no, not competing, but it's just relations and other relations, which is also both of them are true. So which comes from, which I'm going to present from super-Grassmannian. For construction of super-Grassmannian, you know that super-Grassmannian can be described by relations. So we have super Plucker relations. So we have those. And so we have also our version of super cluster structure for that particular example. And so you'll see that, of course, the question is how we can compare and so on. So we'll talk a little bit about those. So to be now a bit less hand-wavy and to be a little bit what's specifically done in this paper. So we defined superanalogues, right, of classical Plucker embedding for the Grassmann supermanifold. So it's a general case. So this target space turned out to be, so we have to do something unusual for that. So we did weighted projective space. So I'll show you how it's constructed. So we figured out what should be super Plucker coordinates, relations for the general case, we have them. Now for particular case, so 2, 0, and 1, we use them to try to propose our own supercluster structure, recognizes the cluster structure, what we think it should be. And now we have exchange graph structure understood for that case. And you will see that there's relations which we obtained for general case. They are quite complicated. So I have some first steps to understand how to simplify these relations. And now the last, there's some comparison you will see with super Ptolemy relations by Bob Penny and Anton Seitlin, and by our super Plucker relations for that case. So that's what's, so it's basically finished and some unfinished result towards this of our project. So, and that's lots of open questions there. So it's just, but some results are finished. Okay, so what is one slide recollection, what's the real, so what is the Grassmann manifold? Of course, you all know, so that's, you have a vector space, right? And the real Grassmann manifold is a collection of all r-dimensional subspaces. So what is the Plucker embedding? You take an element, right? So which is a plane from that space, right? So you fix some basis, and you can see there's a wedge product of these basis vectors. So since you know that this one is defined up to a multiple, then you can define, so this map, which maps L into this wedge product, will be, if you can see the projectivization of that, it will be well defined. Now, okay, so if these guys will be the basis of the ambient space, and you expand your use in terms of those, then well, we can obtain components of Z multivector, right, in terms of basis multivectors. And here one little thing which you which everybody pretty much knows, but we're going to use it, that these components, right, they can be computed as minus of the matrix made of components of this vector written as the rows. So you could see this U1, U1, UR, right? And that these columns correspond exactly for this one. So they're going to be well-known fact. So this minus, well, we denote them by P as everyone else, and they are called Plucker coordinates. Plucker coordinates for that. Now, okay, so obviously, so the elements, so this is an embedding, right? So one can show it's embedding, and the image of that map, so those which corresponds to the planes, these are completely decomposable, factorizable multivectors, right? But of course there are multivectors which are the sums as well. So, and the question is, can we describe the image, right? The image of that map. And famously, it's known, yes, we can. And there is a polynomial equation, set polynomial equations describing that image, which are called Plucker relations. So here they are written in my home notations, which are actually going to be useful later on when I have huge formulas. So it's a home notation. So if you have A underscore it's just for A1 AR. And when I do this in the parentheses, it just means that you say, for example, here's B plugged instead of AR. So sorry, just some home notations, but hopefully easy to remember. So, okay, so then, that's obviously for the basis, we have strictly originally introduced this Plucker coordinates for strictly increasing, but now we can extend by antisymmetry to the all indices because it's just convenient to write formulas this way. Right. Okay, that's what's well known. Now super is a super case, right? So you have now RS, so it's super Grassmannian. We have RS dimensional subspaces in NM dimensional space. So again, you can sort of made up, so L, right? So your element L from that space going to be spanned by R even and S odd vectors. Again, you can, for example, if you want to see the dimension of the space, you can put together this matrix U, where you put your R even vectors first, S, odd vectors afterwards, and then you have this even RS by NM matrix, So then, very similar to this other case, so you can normalize by, you can normalize this basis. For example, I mean, you don't know which columns you can normalize, but for example, the first R and the first S in the odd ones. And then you could see, well, the dimension of that space for this Grassmannian. Now, okay, so so we're going to obviously just imitate what was happening in the classical case with is the simplest way possible. So so first of all, we have to consider exterior powers of our supervector space. So here we have a very classical construction, right? So you take just a tensor algebra and you could, for example, and you can sort of factor it out, quotient it out by anti-continuity conditions, right? So here again, notations, which a lot of people use particularly in physics. So we have I and J, right? Those are even vectors, basis vectors in V. And when you have alpha hatted and beta hatted, they are odd. Okay, hatted and alphas, betas, they are odd. And so you just try to construct very similar, the space is very similar, but just you have slightly different anti-commutativity conditions, right? So the problem is that, and then you say, okay, why not we just L will be mapped into that. So this will be some element of lambda R S plus, R plus of B, right? Now that will not work because of this equality one, if you look at that. So here I just considered this and I just distributed, okay? So what is wrong with that? Well, because of that for the two odd vectors, basis vectors, anti-commutativity going to look this way, this one not going to be zero. And so as a result of that, you don't enjoy anymore this nice property that the top power is always just one-dimensional. It's always just proportional to you know. So you may have these additional terms, and you could see there's no top power because I could keep adding more, multiplying more and more, so you get too many of them. You get infinitely many of them. So the morale of that is that we cannot use it sort of in the straightforward way, but we could notice that the problem here is that only when you have odd vectors generating my plane L. So if my plane is completely even in a superspace, I could still use that. But if my plane is, you know, my plane still have odd vectors generating, I have to use something else. So this construction will be called algebraic case and will work for this case. Now for the RS, so there's another construction. So we have to use another construction, which actually Ted did with Anton Zorich some years ago. So that's introduces exterior powers as well in this sort of axiomatic way. So so there's not much known about this so far. So it's again sort of a collection of open problems. So we said that element of this, what is the sort of RS multivector? That's such function f, which acts on, you know, obviously obvious numbers of covectors, which satisfies the following properties, right? So you have a linear change, you get, you know, just the Berezinian spit out and so on. So important things to remember here, because I want to just make sure that I come back to new things. So okay, so this is generalization of the previous one. If you could substitute zero, can be identified. So you have, well, you have homogeneity in even arguments of degree 1 of -1 here, and you have antisymmetry within each group, and you have linearity only here and not here. So then example, so this is all completely unknown, but we have example of this functions f. So this functions f, so appeared in this, you could see in these papers. So the idea is as follows, right? So, and you could sort of think about this as a nonlinear analog of super wedge product. So you take this R even and S odd vectors, and their wedge product will be a function which defined on the suitable number of covectors as following. You take a matrix Ij, where Ij is, you take Ui and you relate it to Pj's covector. So that will be your Uij's element, and then you compute Berezinian, which is super determinant of that matrix. Okay, so that will be, so this you can show that this satisfies that, so this particular example, and this we're going to use that. So super wedge product, which was going to be, so remember that. Okay, so now so basically we prove the theorem, so that in the algebraic case, when you have R0 planes, you use this, you know, algebraic construction for the exterior power. So we call it lambda R, right, without this one. And you can show that such map, well defined, it's embedding, and the components will satisfy we found. Yes, Ezra.
Can I ask about the previous slide?
Yeah.
Can the functions be taken rational?
Yeah.
Okay.
Okay. So we found, well, that's relations. So, okay, so just to, I know it's very hard to see very fast, but it's just like a Plucker relation spiced up with the science, right? So you have seen that's very similar to the science. So you just, you know, the science quite a bit. So just to, you know, to note that these relations, if you substitute for particular case 2, 0 for 1, which is one of the important cases, corresponds with the works which were obtained by Cervantes, Fiorese, and Yedo in 2011. Now, in the generic case, so in general case, when you have RS planes in an M space, we're going to log in. The idea was original the following. So you take L and you map it in just a in this super analog of wedge product, which is by that formula, Berezinian U times P, right? So it is going to be well defined, but it's not going to give us an embedding. In other words, you cannot reconstruct the plane knowing that. And how to fix it, it requires some fixing. And so easier to see in a small example here. So if you have 1, 1 into 2 Grassmannian, so generated, so here's the basis of V. So let's say L element from here generated by 2 vectors, you can normalize them, for example, in this way, right? We just expand in this vectors, right? So just nothing. So now suppose we have, we know this F, right? So, and this F, this map F, this super wedge product, right? So it's 3 different notations for that. So I just put them all here. Well, right, so we know how its formula, how it's acting on the corresponding number of covectors, right? So that's a general formula. So this matrix U, matrix P, so you have that. Now the question is, suppose we know that, can we reconstruct L, right? Why it's not embedded? Okay, some simple analysis tells you that you can reconstruct X by substituting this covector, so it's just the basis covectors, right? So, and it's similar like in general, in the usual case. So if you substitute E1, E2 hat, then it corresponds to considering this minus, so similar. So 1 over Y this way, so it's going very well. Now, the trick starts here. So when you you need to reconstruct Psi, right, which was that component, yet another component in this matrix U. You will need to substitute odd arguments into even slot. But if you remember that F is computing using Berezinian, and it's also we have multilinearity in even slots, you can extend the definition, but you have to extend the definition to odd parameters, to odd arguments as well. Now to reconstruct eta, you have to yet another trick. It sounds like very similar, but you need to substitute here even in the odd slot, but you don't have multilinearity here anymore. So for that, that was solved. We used that notion, inverse Berezinian, by Bergveld and Jeff Rabin. So who introduced this? So inverse Berezinian is just like Berezinian of parity reverse matrix. But anyway, so it's like a little bit akin of transposition based in my mind. So it's simple, but very valuable operation. So, okay, so then for that inverse Berezinian, it has sort of symmetric properties for the properties of Berezinian. And because of that, it's going to be multilinear in odd spaces. And so you can extend the definition. So that's what basically is the bottom line. So this is how you construct this Plucker embedding. You take this Plucker, but you also have to add, sort of Berezinian and Berezinian inverse of what I call, again, I have home notation, wrong matrices, is where you have an even matrix, but then you plug, well, say here, those who knows about Berezinians, that's not even, right? It's an even matrix, which is spoiled with one vector. And so this is supposed to be odd vector, but it's even, I have no time to explain, but this is supposed to be even vector, but it's odd. So it's an even matrix with one error. So it's like odd. So it's wrong matrices in my notation. Anyway, so I have like this whole results, and this wrong matrices, they are good. They have very interesting properties. They still preserve a lot of good properties of Berezinian, so they're worth to consider. And they pop up in many, many different, somehow important formulas in superworld. So result, yes, as I promised, you map your L into that, right? And that's how you get this weighted projective space, because this comes from Berezinian star, and this comes from Berezinians, and that's why this is weight 1, and this is like weight -1, just from that. Now these are obtained relations. So this will be even relations, and this one, both of them going to be wrong matrices, and so this is going to be odd Plucker relations. So they're big, I understand. I just want to show you. Okay, you could look at them. Okay. Obviously, you can't immediately say that. So a couple of words about that. So that's so that previous result is kind of finished. So with the super Plucker relation, super Grassmannian, it's a finished work. So that's I would say nothing to add much here. But now the questions are, so if we want to use them for some construction, so a lot of you, if you know that this stuff, you would start to think, can we simplify them somehow? That looks like it's the first thing that would pop up. So I actually worked on simplification of that particular one for the case when you have one here and one here, because actually Greg Musiker from that, remember that competing team asked me what's going to happen with the dual case, because he wants to see like, because we know the dual going to be such, just he wants to see the relations and just see what do you have. So, and because of that, I worked a little bit on them. So anyway, so I figured some new set of coordinates, which are going to be anti-symmetric in all indices. I don't have time to talk about this, but bottom line is some nice trick where you could actually introduce, which requires some interesting things, which actually allows you to write down in quite a nice form these relations for this dual case. And I'll show you for some particular example, because it will be even nicer. So they look like this. So theta stands for odd coordinates, and P for even. And now what my pride is that they all anti-symmetric in all indices, even the thetas. So that's a beauty. And those who work in cluster algebras, or at least what I do, it's very important. This anti-symmetry is useful to reductions and some other stuff. So at least what I use. So then, okay. So then. Briefly, so that's as you know that you have heard already about a little bit of cluster algebras. So I'm going to introduce it's just a commutative algebra, right? So it's a big story. So I can't tell much about this. But okay, due to Fomin-Zelevinsky in 2002, so you have a commutative algebra with a family of distinguished generators, which are grouped into overlapping subsets, and you can get one from another. So here because I'm going to generalize this case, this particular example. So, you could sort of think about this. So this is a classical example. So the homogeneous coordinate ring of Grassmannian 2n, that's a famous example of the polynomial, of the cluster algebra. And so the idea is, okay, for example, one way of, like I like to, when people explain that, is the following way. So you have 10 coordinates here, right, in this case. And for example, you want to know what if when you want to check positivity of all 10 coordinates. And one way of doing this, you immediately notice that, okay, you don't need to check positivity of each of them, but you can kind of, because you have also relations of certain kind, you can bypass skipping some relations, right? Skipping some of the coordinates. It turns out that it's enough this and this, if you're mechanically working on this, like sort of like one small high school competition problem. So you get like that these are different, which are enough to check, right? And then you see, okay, how they're different. And you see there are some common parts of them, and you can order them in such a way that each time they just change by one. And that sort of give you, like, if you don't know cluster algebras, give you idea how they all, so the classical model examples. And each time you go from here to here, it's called mutations. You mutate, and mutations are governed by these relations coming from Plucker relations you express. But each time important, you express the new cluster variable in terms of old cluster. So that's what pretty much is coming from. Okay, important thing about Grassmannians, this Grassmann cluster algebras, is what it's have a beautiful representation. So it can be parameterized by triangulations of the regular n-gons. So in our case, it's 5-gon because I taught it in 5 dimensions. So it's a 5 gons. So every cluster, it just represents. So here's a cluster 1, 3 and 1, 4, and this one are frozen variables which don't change. There's a side they're represented by P1, 5, P like 4, 5, and so on. So, and this one are mutating. So the ones which in mutations or going from one cluster to another goes just, by flip, by topological flip. So you flip, and so, and then so that's a very beautiful construction. Now, what happens in our case? In our case, we have, if we consider to restrict our relations for this particular situation, we have so many relations. So, so actually from these ones, we can get rid of, because, you can, in every chart, you can solve for, for TAB, and in every chart, you have invertible, one of this TAB invertible, and then you can solve for T1 hat, 1 hat, which is even, but it's an nilpotent, so it's not very nice. So, but you could solve for it, and then you kind of can consider all of them, you could forget about them. So you can consider just 20, 21. So this, in this case, you're going to be just having this even Plucker relation and odd Plucker relation. Now, we want to look at them and recognize a structure, something similar like you saw, the cluster structure, something similar of that. But the question was where to put the odd variables, what to do with them. And so idea is that geometrically, symbolically, it's very easy, like geometrically, it's very easy to see. So that what the idea is the following. So you take the triangulations, but you decorate one of the variables with dots. And these dots will be representing the odd variables. So that's a structure we think we see in that. So for example, here, so in this case, right, you have every cluster going to have as many even variables, so it's how many diagonals, proper diagonals, and you have one of distinguished, which will be decorated by, and that's going to be, so the cluster going to look this way, okay? And in the cluster algebra, it's important how to go from cluster to cluster, so it's called mutation. And the mutation is going the following way, so we have, okay, in our case, we propose to have two types of mutation. One is called odd mutation, which just jumps, which allows to jumps the red into the odd variable into nearby vertices in such a way that it's still decorating one of the diagonals. And well, you can express, you can express the new using this odd Plucker relations. You can express the new odd variable in terms of old ones. Okay. And okay, so here I don't know how much time I have. You should supposed to be.
So you started a little late, but let's say 21 minutes.
Oh, okay. So I have plenty. Okay. So I think I was rushing up because I was worried. Because I was like thinking, okay, I am okay. I have plenty of time. Anyway, so I can show you, but maybe still I don't know. It's just maybe sounds a bit technical for people who didn't see a lot of cluster algebras. But it's what I want to say that okay. So there is a small thing I still can show you maybe here. So that which is discussed in this field, but all of you can understand that. Because originally, when we obtained geometrically, right, this, well, Plucker relations, super Plucker relations, right? We have something like that. I rewrote it, just put them all in one side, just, yeah. But geometrically, you all work in sort of anti-symmetric notations, right? So this is the natural notations we have, right? But when you go to the, say, cluster algebras, when you start to do this, this with polygons and everything, you start to use with strictly increasing, right? So the question is, well, you start to have some negative signs, and in this world, it's important when you have negative or positive because you can study, there's lots of things you can study, say positivity and other stuff. So this negative signs is important in that world, so they can spoil things, right? And so that's the question. So do you have negative or positive? And so here I have some little analysis for the odd, what happened with the odd mutations, right? And so I figured the following. So you have that linear ordering of the vertices, which is given to you. So that odd mutation always happens within triangle, not happening within quadrilateral, but happens within triangle. And in fact, the formulas for theta C, it doesn't matter whether it's on this or this mutates into this or this. The formula is the same. But it's all happening. So the order, linear order on the polygons implies the order on this. So the ordering is one of those on the vertices. And then then what we can do going from anti-symmetric to the strictly increasing notations, right? So we have this generic form. We can express our theta C into here as this one. And then obviously just substitute it, like moved it. And then you see that the signs pretty much, if C is in some extremities relative to A and B, into which it's mutate, we get minus sign somewhere. But when C is in between, you have like, obviously it's plus sign because minuses are canceled, right? Okay, so that's a small one thing. You'll see why I'm talking about this. And then we have even mutation here. So remember that we have odd mutation, which just jumping the dots, right? Now the even mutation is the whole diagonal, is the flip, like old flip, topological flip as you know it from other stuff, but you dots also going together, mutation, decorations goes together with diagonal, okay? So for that, remember that there's a story that you have to explain, you have to express the old, so the new variables, cluster variables in terms of old. And you use these relations for doing that. And what I have a little analysis, and pretty much you're always going to have, because of this one going to be between, this one sign is going to be plus, another sign going to be negative, always. This is, of course, a particular example, but you're going to have it always this way. So yeah, so there's some. So what's happening now for the general case? This is as opposed to the general cluster. So in general, they only have, in the classical case, they only have an even Plucker relation, which is this. And you say, why don't they have the same problem? But you may know that if you start to do, because you only have cyclic permutation because of the ordering, you're going to have all the times the same. Some negative signs, of course, will appear, but they will cancel out. So you always have the same relation. So they never have a problem with that. So that's this. So now about exchange graph. So what's exchange graph? Is it like here? So they want to see what's going to happen if like you change, like you start with some triangulation. So the beauty of this whole cluster algebra is lots of interesting properties, but one of them say you start with one of those clusters, and by this mutation, you can get everything else, all the other clusters. And so remember that this is all parameterized, this all by triangulations. So they study this because it's homogeneous space when you say like so one orbit. So you can study how this exchange graph look like, how this orbit look like, right? And so so that's called exchange graph. So in our case, okay, so what I understood that our cluster algebra, supercluster algebra example, going to be the exchange graph, going to be a blow up of the classical exchange graph. So what happens, maybe I can show the next slide, is that this is what in cluster algebra everybody know for the case of GR2, 5. So they know that there's only 5 different triangulations, and they're going to be like and this by coincidence also a pentagon, right? They love it. And then what you have here, you have a blowing up at every point, and every point here you have odd, so it corresponds to the same triangulations, but different decoration, different dot decorations. And so you can show that it works for every case. And I can show a more interesting example because it looks more interesting. So that happens. That's also for those who in cluster algebra, they know it's very well. So that's exchange graph for 2, 0, 6. Well, they called so 2, 0. Sorry, exchange graph for this one, 2 in 6, right? So they know this is how the orbit, how they're going to mutate, right? So one triangulation, another, and so this is a structure. And here, that's how blowing up goes. So instead of this, I have 3. So this corresponds to the same triangulation, but decorations are different. And you do this at every and that's become, even I could show you here, zoom up, right, to the same thing. So if you look at this plot, that is, well, it's demonstrated here, right? So you see the same triangulation, but the dots, this dot jumps just here, then it's jumped here. And this one, this corresponds to this one here. You mutate, it's the same triangulation. So that's, and you could think, after it presented this way, you can think, oh yeah, that's it's more or less clear how wide it should be in the general situation, right? One thing. But I had this question for a while. Now the answer is simple. Yeah. So you could do that way. So now the last actually thing, I'm almost at the end. So remember there was a story, right? So there's another very powerful example. So it's coming from, so there's this global coordinates for decorated super-Teichmüller space, right? So they were introduced by Penn and Sentlin, and very interesting. So they wrote down this super Ptolemy relations, which this global coordinate should be satisfied. And this group, so originally from Minnesota, now in different spaces, now Nick moved to other university, they built their cluster, supercluster algebra based on those relations. Now I'll show you these relations, and you could see why we are so sort of some interesting sort of discussion could be, because the relation seems to be similar to what, but different, similar but different, and they all come from yeah. So I can show again. So yeah. So this is for particular case. This is our relation, but you can write this for A, B, C, whatever, right? And they have relations, this ones, which is, yeah, we come down to simple formulas, but so for the classical case, Plucker relations and Ptolemy relations, they're the same. And they're the same as in you know, Euclidean theorem, you know, you can circumscribed quadrilateral, and then the product of the diagonal equal to the sum of the opposite. So it's also coincide with that. But with super situation, we seems to be, two different areas, and then relations become different in super situations. There's this and that. So the question, yeah. And so result. So the question, of course, everyone asks us how they compare. And so what I figured is a small change of variables. So the E and F is the ones which corresponds, is the letters which symbolize the diagonals. So if we do the change of variables, this one, so certain change of variables, then you can show that if you consider the product of the new diagonals, you get what that. Now, so there's lots of discussion about this, of course, because I did it only locally, because remember that like you have lots of triangle, like quadrilaterals, it's like, can I do it like extend it all? Well, it'll be like, I don't know any answers to that. It's again one of these openness. I don't know. I just noticed that you could do this, and whether it's just was to mention that we can do it, but it's still very open. Lots of open questions here. Why and that. So and here's like works. Main works of this competing group. So it's not competing. It's actually definition of the cluster algebra one competing definition. So this is example, right? So this is Valia with Misha is their definition of supercluster algebras also. And then just read Penner. So, but it's actually cut off from the print. So yeah. So yeah. So Bob Penner's and Penner. So this is where the super Ptolemy you can find their relations, and this is two works on which this my and Ted's result are based on. So, and thank you very much. I'll stop here.
Thank you very much. That's fascinating. Please go. Thank you very much, and we have some time for questions.
So you had this picture of when you do the even flip, and you also move the two dots with the odd variables with it. And similar to the super Teichmuller relation, you have one of them with a plus sign and one of them with a minus sign. How do you decide which one gets the minus sign from the picture?
Okay, so well, as I said, so here, okay, so here's what's happening. Because I just realized that they're going to be unique, determined, once you have, which is the usual case, once you have ordering of the vertices. And in the following way, which actually I was thinking about this. So here's an example. So everything happening within good quadrilateral, right? So once you order the vertices, because it's part of that, you're going to have only, the same ordering in the quadrilateral, the same ordering. Now, because of that ordering, you're going to have basically they impose the signs already on the relations. So they will give you the signs once you impose the ordering. Okay, once you impose the ordering here, they will give you the signs. So that's I know that we discussed it for quite a while, but then I just said after we get ordering, we get the signs. And they start with the ordering. I think you have to have the ordering in the original one. So that's geometrically you could immediately see it that way. So.
Are there any questions in the Zoom? No. Any more questions from the audience? All right, then I thank you very much, and thank you for a great talk.